afternoon. Climate changes can impact watersheds with drought conditions with very little rainfall or excessively wet conditions. Resilience in a watershed means that the watershed adapts well to climate change impacts. The main stream keeps flowing during drought periods, and that's because it has a high groundwater storage capacity. Therefore, it also has a high base flow percentage of its total flow from the watershed. It also has the ability to absorb floodwaters. Overbank flooding impacts are minimized and flood damage is reduced in a resilient watershed. If we look at the precipitation at State College over 74 years, we see that the average is 40.66 inches, and 2018 had 63.75 inches. The red ellipses show periods of below normal rainfall, and the blue ellipse circles 5 years where rainfall was particularly above normal. Homing in on 2018 as an example, the 30-year average precip was 40.66 inches, and it was exceeded by 50%. Of that 50% excess rainfall, groundwater recharge swallowed up 11.93 inches. That caused the water table in the watershed to rise over 66 feet, and that amounted to 36 billion gallons of groundwater storage. The blue bars show the monthly average precipitation throughout a year, and I want you to note that there's not much variation between the wettest month, August, and the driest month, February, less than 2 inches of variation. The orange bars show the extreme amount of precipitation received during 2018, where in July, August, and September, the water table level shown by the blue line rose tens of feet, and the 66-foot rise I referred to is the accounting of 36 billion gallons of groundwater storage. This groundwater storage into the following year, 2019, didn't decline very much because of the capacity of the storage within the major aquifers. The karst characteristics in the Spring Creek Watershed involve groundwater piracy, where groundwater recharge and flow is stolen from the headwaters area adjacent recharge watershed of Spruce Creek. That makes the groundwater watershed of Spring Creek 23% larger than the surface water watershed. The Gatesburg Formation has approximately 3 times more storage capacity than the other carbonate formations and accounts for a lot of the recharge capacity in the watershed. In the Gatesburg Formation is located Big Spring in Bellefonte that flows at 14 million gallons a day, making it the second largest spring in Pennsylvania. Very importantly, mountain runoff into sinkholes from the shale and sandstone ridges that surround the carbonate valley floor causes surface water to immediately become groundwater once it leaves the stream and enters the subsurface. One of these major streams distributes recharge out onto the valley floor, and there is a large area in the watershed of high infiltration capacity soils that is an unusual characteristic in a karst watershed. The star indicates the location of Beaver Stadium at State College, Pennsylvania, and the blue line delineates the groundwater watershed boundary of Spring Creek. The yellow shading shows you the carbonate valley floor area, and these 20 arrows all indicate mountain streams that are running off the mountain ridges made up of shale and sandstone, and at the point of every arrow is a recharge area that either swallows part or all of the flow of the stream off the clastic rocks. The double red circles indicate well fields accounting for the 16 million gallons per day of groundwater pumpage, and they're all located within the carbonates in the valley floor. The blue shaded area is the surface water watershed area of the Spruce Creek adjacent watershed, and the white arrow shows you the flow direction of the streams in the Spruce Creek watershed. The black dashed line is the location of the Birmingham thrust fault, and that high permeability zone within the watershed steals the groundwater recharge from the Spruce Creek watershed surface water boundary area. This high amount of storage accounts for greater than 93% base flow of groundwater as a percentage of total flow annually discharging from this watershed. Here's a subsurface cavernous zone illustrating the conduits that are carrying the 14 million gallons a day, the distance of 15 miles from the headwaters recharge down to Big Spring and Bellefonte. The white line indicates a surface stream recharged by mountain runoff and flowing out onto the carbonate valley floor. The star symbol is a sinkhole location that swallows part or all of the flow of the stream at various times of year. The tan shaded area is the area of high infiltration capacity, very sandy soil overlying the Gatesburg Formation that is an unusual characteristic for a karst groundwater watershed. We're going to take a look at the area in the red ellipse, and the arrow shows the stream flow, and The cloud symbol represents mountain ridge recharge, which provides the headwaters area for this stream, and it's a losing stream flowing out onto the valley floor. This picture with the dashed red line shows a sinkhole that is taking 100% of the flow of this stream at a time frame about 2 months ago. So the blue arrow shows the surface water flow into the sinkhole area, and the stream does not continue beyond the swallowing in this sinkhole. This picture shows the same sinkhole area shown in the red dashed line in the summertime, with no flow making it out onto the carbonate valley floor area, and so the stream bed is dry. The blue arrow shows the flow of the stream in the summer, again being swaddled completely into the same sinkhole in the stream bed. The red dashed line outlines the submerged sinkhole in this 2018 photograph during high flow in the stream, when water bypasses the sinkhole because the flow of the stream exceeds the acceptance capacity. The inset diagram shows that it's a losing stream, and groundwater is recharging in the sinkhole at a rate of tens of gallons a minute, and also recharging groundwater by leakage through the bed of the stream. The high precipitation, setting the record for annual rainfall in 2018, caused this stream to also exceed the infiltration capacity and bypass the sinkhole with some of its flow. Looking at this 50-year period, we're going to plot mean annual discharge in cubic feet per second against total annual precipitation in inches. So here's the variation in mean annual discharge over this 50-year time period, and the dashed line shows the 93% average base flow percentage of the total flow over this time period. The orange line is the precipitation in inches each year, and you can see that the stream flow follows the precipitation in a quite a regular, correlated fashion. The shaded orange areas represent periods of a dry spell of a year or two or three or four where precipitation is below normal. And what I've placed them on this graph to show is how little the stream flow drops compared to the disproportionately greater drop in rainfall during these dry spells. Plotting the average annual depth of the water table in feet against the total annual precipitation in inches, we have again a high correlation where the orange line here has 2 very wet years back to back, causing an exaggerated rise in the water table level in the watershed. Here again, the orange shaded areas represent periods of below normal precipitation, and the green areas show the areas of above average groundwater table level throughout the watershed. And as I said in the beginning, the stream flow is supplied from the groundwater storage in green, and this graph shows how little the stream flow drops in the orange periods of below normal precipitation. The blue shaded area highlights the groundwater storage supplying the average annual stream flow during the periods of below normal precipitation, making this watershed stream flow very resilient to drought conditions and to periods of excessive rainfall, as shown by the graph for 2018. To summarize, 63.75 inches of precipitation fell in 2018, and that was the wettest year in 125 years of record. The sinkholes and the sandy high recharge capacity soil throttled 36 billion gallons of recharge, and that caused very limited overbank flooding in spite of the excessively high rainfall. So this demonstrates how the Spring Creek Watershed has a unique combination of its karst, structural, and residual soil characteristics. And it has an excellent groundwater recharge capacity and an excellent groundwater storage capacity that together make it very resilient to the impacts of climate change. Thank you.